So 2 instead of 3, just to make sure I fall within the canonical stopping time. So the goal of my talk is to consider 2 principles that guide research in quantum gravity from the point of view of a particular approach, the condensed matter approach. I'm going to begin by identifying 2 distinct versions of this approach, and then I'm going to consider the extent to which the principles of asymptotic safety and relative locality can be supported by these versions. So the general hope is that a focus on distinct versions of a particular approach to quantum gravity might provide some insight into the nature of these principles. So to set the stage, let me first address 2 questions. And the first is, why are guiding principles of interest in quantum gravity? Well, simply put, there is currently little contact between theoretical work in quantum gravity and empirical tests, as this recent review makes evident. So, quote, unfortunately, in spite of more than 70 years of theory work on the quantum gravity problem and a certain proliferation of theoretical frameworks being considered, there is only a small number of physical effects that have been considered within quantum gravity theories. Moreover, most of these effects concern strong gravity, large curvature contexts, such as black hole physics and Big Bang physics, which are exciting at the level of conceptual analysis and development of formalism, but of course are not very promising for the actual experimental discovery of manifestations of non-classical properties of space-time and or gravity. So given that guiding principles are a necessary aspect of research in quantum gravity, why stress 2 particular ones? Well, the short answer is that I find these 2 particular principles relevant to the condensed matter approach. Moreover, while philosophers have initiated discussions for such principles as holography, as yesterday's talks indicated, background independence, and various other ones, little has been said about asymptotic safety and relative locality. So let me begin by briefly reviewing these 2 principles. So the first is asymptotic safety, and this requires that a theory of quantum gravity must scale towards an ultraviolet fixed point with a finite number of UV irrelevant couplings. So I'm going to try to explain what this means, at least to the best of my understanding, in just a few minutes. But the general idea is that this is supposed to address a particular problem with reconciling general relativity and quantum field theory. In particular, when GR is formulated as a quantum field theory, it's non-renormalizable. Now, in this context, this means that when you expand the relevant quantities in GR in a perturbative power series expansion, there are terms that diverge at high energies and that cannot be regularized by renormalizing a finite number of parameters. Now, this has led some authors to view GR as a non-fundamental effective field theory. But Weinberg, however, suggested that if general relativity could be shown to be asymptotically safe, then it may warrant the ascription of a fundamental theory after all. So being clear about the principle of asymptotic safety will require being clear about the notion of an effective field theory, which plays an essential role in the condensed matter approach. Moreover, the distinction between an effective field theory and an asymptotically safe theory raises important questions like what is a fundamental theory? So the second principle I'd like to consider is relative locality. It requires that a theory of quantum gravity must entail that coincidence of events in space-time is relative to an observer's rest frame. Now, this is motivated by its advocates by taking seriously the nonlinear composition law for velocities in special relativity. So this law imposes an invariant scale, the speed of light, c, on the theory, and this scale makes possible the mixing of spatial and temporal coordinates. And the mixing then entails the relativity of simultaneity, right? The relativity of coincidence of temporal events. If one assumes a similar nonlinearity in the composition law for momentum, one is led to an invariant scale for energy momentum, and a corresponding mixing of spatio-temporal and for momentum coordinates. And then this mixing is supposed to entail the relativity of locality. So one motivation for introducing an invariant energy scale is that it can be associated with a Planck mass, and then one can characterize the relativity of locality as an effect of a particular regime of quantum gravity.
So who's an advocate of relative locality?
Oh, Lee Smoling and some of his co-workers, and a couple of fairly recent. Well, there are a number of articles that have been published in the last couple of years on this stuff.
I believe Amelino Camellia, right? Who was the first one to propose it?
Yeah. All right. So another motivation for introducing an invariant scale is that nonlinearity and momentum composition can be encoded in as curvature in momentum space, and this is suggested to its advocates that space-time emerges from a more fundamental energy-momentum reality. So relative locality seems relevant to the condensed matter approach insofar as topological invariance in momentum space play significant roles in various examples of the condensed matter approach, and topological invariance can be related in various ways to momentum space curvature. Moreover, this principle raises the question, is a state space of a physical system in terms of energy and momentum variables more fundamental than one in terms of space-time variables? Okay, so I'd now like to move on to considering the condensed matter approach in just a little bit more detail. So the goal of the condensed matter approach to quantum gravity is to construct an effective field theory of a condensate that mimics general relativity and the Standard Model. Now, one way of understanding the nature of an effective field theory is by means of the concept of a renormalization group transformation. And this essentially involves three steps. Given a theory encoded in an action S, one first separates the field variables into low and high energy modes, typically with respect to a cutoff, and then one integrates out the high energy modes. That's the second step. And this typically results in an action that is formally distinct from the original action. One then attempts to absorb these changes into redefinitions of the couplings to restore the original form of the action. That's the third step. Now, if all three steps are possible, then successive iterations of such a transformation generate a flow in the abstract parameter space of the theory, a renormalization group flow, and a fixed point of such a flow is a point that's invariant under further transformations. Right? So at a fixed point encodes a theory with scale invariant parameters. So I take at a fixed point, not only does the form of the action remain invariant, but so do the values of the parameters that appear in it. One can stop at the second step of this process. The point about which the low energy degrees of freedom are expanded defines a fixed point in the renormalization group flow. And in most applications, one can assume interactions are weak, and the fixed point can then be identified as the Gaussian fixed point that defines the free theory. So the expansion is then understood as a power series expansion in small perturbations about the free theory. So in general, an effective field theory can be understood as a low energy expansion of a theory about a fixed point in a renormalization group flow. Now, two additional features of fixed points will be relevant to what I have to say next. The first is that a fixed point defines a universality class, which is an equivalence class of theories that possess the same behavior in the neighborhood of the fixed point. And second, condensed matter systems that exhibit phase transitions are typically described by theories that possess fixed points. Such a fixed point determines the values of the theory's parameters at which the symmetry that characterizes the system's internal order is spontaneously broken. And the main point here is that not all condensed matter systems have these features associated with renormalization group fixed points. Now back to the condensed matter approach. Recall the goal is to construct an effective field theory of a condensate that mimics general relativity in the Standard Model. You can now identify two distinct versions of this approach dependent on the type of condensate one focuses on. One version, call it version A, focuses on condensates that can be characterized by spontaneously broken symmetries and universality. An example of this version is Belovik's effective field theory of superfluid helium-3A, he demonstrated that it belongs to the same universality class as the massless sector of the standard model above electroweak symmetry break-in. So the essential features of this version are that the effective field theory is characterized by universality, and the internal order of the condensate is characterized by symmetry. Well, there's a second version can be identified, which focuses on condensates that cannot be characterized by internal symmetry. Rather, they're characterized by what Wynne has referred to as topological order. So an example of this version is Zhang and Hu's effective field theory of the edge of a four-dimensional fractional quantum Hall liquid. They showed that it describes 3 plus 1 dimensional zero rest mass fields of all helicities. So the hope then is that general relativity in the standard model can be reconstructed from zero rest mass fields, perhaps by using twistor methods. So in this version, the concepts of universality and order characterized by symmetry do not apply. Right? Rather, internal order is characterized, again, by what Wynne has referred to as topological order. Okay, so two versions of the condensed matter approach. Now, I'd like to return to these the two principles. First, the principle of asymptotic safety in just a bit more detail. Recall that it requires a theory of quantum gravity must scale towards a UV fixed point with a finite number of UV irrelevant couplings. So what's a UV fixed point? It's a fixed point associated with high energies, with the renormalization group parameter a little less going to infinity. And infrared fixed point, on the other hand, is a fixed point associated with low energies. An irrelevant coupling with respect to a fixed point is a coupling that decreases towards the fixed point. So a UV irrelevant coupling decreases at high energies, whereas an IR irrelevant coupling decreases at low energies. And in contrast, a relevant coupling with respect to a fixed point increases towards the fixed point. So a UV relevant coupling increases at high energies, an IR relevant coupling increases at low energies. These distinctions then allow one to characterize theories in the following way. A renormalizable theory is associated with an IR fixed point and possesses no IR irrelevant couplings and a finite number of IR relevant couplings. A non-renormalizable theory, on the other hand, is a theory associated with an IR fixed point and possesses an infinite number of IR irrelevant couplings and a finite number of IR relevant couplings. Along these lines, Weinberg defined an asymptotically safe theory as a theory associated with a UV fixed point and possessing a finite number of UV irrelevant couplings and a potentially infinite number of UV relevant couplings. From this point of view, an asymptotically safe theory is essentially the UV mirror image of a non-renormalizable theory. So an example of a non-renormalizable theory, again, is general relativity formulated as a quantum field theory. When it's so formulated, turns out it has an infinite number of IR irrelevant couplings that supposedly blow up at high energies. An example of an asymptotically safe theory is quantum chromodynamics. The UV fixed point of QCD is the free theory, right? The strong force goes to zero at high energies. So not only is QCD asymptotically safe, it's also asymptotically free. Weinberg originally suggested that general relativity formulated as a QFT might be another example of an asymptotically safe theory. Right? So if it has a UV fixed point, not necessarily a Gaussian fixed point, then its IR irrelevant couplings would be tamed and the theory would be well behaved at all scales. This suggestion by Weinberg has spawned a research program that attempts to identify UV fixed points of general relativity and thus the associated guiding principle of asymptotic safety. All right, so An initial assessment of this principle in the context of the condensed matter approach might begin with the following claim. The effective field theories in both versions of the condensed matter approach should aspire to be asymptotically safe, at least to the extent that they attempt to reproduce the QCD sector of the Standard Model and possibly the general relativity sector of quantum gravity. So this would seem to mean that the effective field theories in both versions aspire to be associated with two fixed points. Right? An IR fixed point associated with the theory of the high energy condensate, and a UV fixed point associated with the QCD and possibly GR sector of quantum gravity. So one potential worry here is whether it's consistent to consider an effective field theory as asymptotically safe. Right? Under Weinberg's interpretation, an asymptotically safe theory is fundamental to all orders. An effective field theory, on the other hand, is typically not taken to be fundamental in the same sense. Right? It's supposedly restricted to a given energy scale beyond which new physics is supposed to arise.
Do you want me to wait to the end, or can I?
No.
So, sorry, maybe I missed something. What's like? I mean, normally thinking about QCD and GR as quantum field theories, I mean, they don't have. So GR may or may not, whatever quantum gravity is a field theory may or may not have a UV fixed point, but the trivial fixed point isn't a fixed point. The trivial fixed point is not a fixed point of the theory. So how would there be like one UV fixed point for the two theories? You know what I mean? So I mean, the fixed point for QCD is like the trivial one, but that's not a fixed point for.
Yeah, I see what
we
you
can
mean.
come back to that. Okay.
Maybe I shouldn't put that under concern.
Okay.
Right, so you're saying the QCD fixed point, the UV fixed point is the Gaussian fixed point,
right.
Whereas Weinberg's suggestion is that it's not. It's
yeah.
Are you asking in the first yellow box and the second line, what does it really mean, fixed point associated with? That's my question to you. Is that what you're saying?
Yeah. I mean, I know what the fixed point associated with QCD is, but both of them.
Okay, so continuing, there's this tension between an asymptotically safe theory as supposedly fundamental and an EFT as at least typically understood, not fundamental. Right? So, for instance, in the condensed matter approach, one might identify the fundamental degrees of freedom as those of the condensate, whereas the degrees of freedom associated with GR and the Standard Model might be taken to be low-energy approximations to the more fundamental degrees of freedom. So in what sense would the AST associated with GR, possibly in the Standard Model, and QCD be fundamental? The relation between an effective field theory and its high energy theory, I would argue, does not have to be interpreted as one of approximation. For instance, suppose one can cash it out in terms of an appropriate notion of emergence. Then perhaps it would be consistent to maintain that an asymptotically safe theory can emerge in the form of an effective field theory of a fundamental condensate. So suppose, for instance, that an effective field theory exhibits a failure of law-like deducibility in the sense that the phenomena described by an effective field theory are not deducible consequences of the laws of a high-energy theory. Now, this is suggested by the fact that the Lagrangian that describes an effective field theory, the Lagrangian that describes an effective field theory and the Lagrangian that describes its high energy theory, the associated high energy theory, are typically formally distinct. Perhaps that suggests that the laws that associated with the effective field theory and the high energy theory are distinct enough to identify, to entail a failure of law-like deducibility between the two. Suppose further that an effective field theory exhibits both ontological distinctness and ontological dependence with respect to a high energy theory. Ontological distinctness insofar as suppose the effective field theory degrees of freedom characterize physical systems that are ontologically distinct from those characterized by the high energy degrees of freedom. Ontological dependence insofar as the physical systems described by an effective field theory are ontologically dependent on those described by a high energy theory. Supposedly. So these characteristics might then underwrite a notion of emergence based on novelty, underwritten by the failure of all reproducibility, and microphysicalism, underwritten by ontological distinctness and ontological dependence. This talk really isn't the place to argue for this particular interpretation of effective field theories. I've tried to argue for it elsewhere. But I guess my main point here is if one desires to construe an effective field theory as asymptotically safe, then perhaps some sort of story along the lines of emergence may have to be told. But let me move on now to the second principle. Second principle is relative locality. Recall, this requires that a theory of quantum gravity must entail that coincidence of events in space-time is relative to an observer's rest frame. Now recall that the idea here is that this is due to a nonlinearity in the composition law for momentum, and this nonlinearity can be encoded in momentum space curvature. Now, to see how relative locality arises as from curved momentum space, advocates of relative locality tell us to consider the phase space for a single particle according to special relativity and general relativity. So in both cases, the canonical variables are the positions and form momenta of the particle. Right? In special relativity, the phase space is given by the Cartesian product of configuration space and momentum space, where configuration space is taken to be Minkowski spacetime. In general relativity, the phase space is taken to be the cotangent bundle over configuration space, where now configuration space is taken to be a curved Lorentzian manifold. Now, in both cases, momentum space is assumed to be flat. In contrast, the momentum space of a theory that satisfies relative locality is assumed to be curved, and its phase space is then given by the cotangent bundle over momentum space. So in a theory that satisfies relative locality, there's a separate space-time for each point in momentum space. And if momentum space is curved, then the space-times will differ from point to point, and that's supposed to be a manifestation of relative locality. So one motivation for taking momentum space curvature seriously is that it entails non-commutativity of space-time coordinates, and there are various approaches to quantum gravity that employ non-commutative geometry. Another motivation is that momentum space curvature encodes corrections to relativistic particle dynamics on the order of the relevant energy scale divided by the Planck mass. And these corrections may have measurable effects at low energies and long distances. So for instance, Amelino, Camellia, and Smolin have argued that the time of arrival of gamma ray bursts as measured by the Fermi telescope may display one such effect. So how does relative locality relate to the condensed matter approach? Well, according to Amelino, Camellia, and co-workers, just as some condensed matter or fluid systems possess analogs for relativity and gravity, it may be that condensed matter systems with curved momentum spaces may give us analogs to the physics of relative locality. So I'd now like to consider the extent to which both versions of the condensed matter approach are characterized by curved momentum spaces. So it turns out both versions, well, sort of the canonical examples of both versions encode aspects of their effective field theories and aspects of momentum space topology. Then these latter can be related to momentum space curvature. So very broadly, an example of a relation between topology and curvature is the Gauss-Bonnet-Chern theorem. All right, so this relates an aspect of the topology of a given parameter space to an aspect of its geometry. So I think the idea is that in both of these, my claim is that in both of these versions of the condensed matter approach, you can identify relations that are similar to the Gauss-Bonnet-Chern theorem. Relations that relate aspects of topology to aspects of curvature. The first version does this in 3 steps. So first, it encodes low energy dynamics in the form of a Green's function on momentum space, where the form of the Green's function just depends on the condensate's Hamiltonian. So for the example of superfluid helium-3A that Belovic discusses, low energy excitations correspond to poles in the Green's function, and these poles define points in momentum space, what are referred to as Fermi points. Belovic then demonstrates that the low energy dynamics is stable under perturbations. And he does this by constructing a topological invariant, called script n here. It's given by the integral in momentum space over a surface sigma that encloses the Fermi points, where the integrand just depends on the Green's function and derivatives of its inverse. So it turns out this defines a non-trivial Winden number of the map from sigma to the space of Green's function matrices, and this map is an element of a non-trivial homotopy group. So this means that script n is invariant under continuous deformations of the Green's function, and the interpretation then is that this entails it's invariant under low energy perturbations of the Hamiltonian. So one finally needs to relate this topological invariant to momentum space curvature. So intuitively, the topological invariant is another example of a relation between a topological invariant, a feature of topology on the left-hand side and a feature of geometry on the right-hand side. Specifically, you can show that in the specific case of the integer quantum Hall effect, the quantized Hall conductance, sigma, is given can be encoded in a topological invariant that you can obtain from the script n thing by a particular process. And it's been shown that the Hall conductance can be encoded in the adiabatic curvature of the relevant parameter space. So this suggests that the integral expression that defines script n in our case also encodes parameter space curvature. In the second version, similar steps can be identified. So in this second version, one first encodes the internal order of the condensate in its ground state degeneracy. Now the canonical example here is that of a fractional quantum Hall liquid, and Wynne showed that 2 distinctly ordered fractional quantum Hall states given by distinct filling factors can have the same symmetries but different ground state degeneracies. So this suggests that the internal order of fractional quantum Hall states cannot be characterized by symmetry, but can at least partially be characterized by ground state degeneracy. And then one can demonstrate that the ground state degeneracy of fractional quantum Hall states depends on topology and is robust under arbitrary perturbations, which indicates that it can be encoded in a topological invariant. And finally, one can relate ground state degeneracy to momentum space curvature in the following way, according to Wynne. He showed that fractional quantum Hall states can be classified by matrices, K, and described by an effective topological quantum field theory, a Chern-Simons theory. Here the determinant of the matrix encodes the ground state degeneracy of a given fractional Hall liquid, And finally, Wynne showed that the matrices can be encoded in the Berry phase, characterizing adiabatic deformations of the fractional quantum Hall Hamiltonian. And the Berry phase is an ingredient in the definition of adiabatic curvature. In these ways, both versions of the condensed matter approach may be said to satisfy relative locality, to the extent that they encode relevant features of their effective field theories and topological invariance, and you can relate topological invariance to parameter space curvature. So maybe a bit more conceptual.
Sorry, did anyone investigate whether you can see also the corresponding non-commutativity in space-time coordinates in these examples?
In what?
In these examples, you've shown that you can see momentum curvature. Can you also see, and maybe through the, find the physical effects of space-time non-commutativity corresponding to that momentum curvature?
Oh.
Because as you said in the previous slides, if momentum space is curved, then coordinates do not commute.
Yeah, not that I'm aware of.
No?
Okay, so advocates of relative locality suggest that it entails what is fundamentally real is neither space-time nor momentum space, but phase space. So we get statements from Emilino Camiglia and co-workers in at least two papers of the following sort. We do not live in space-time, we live in Hilbert space, and the classical approximation to that is that we live in phase space. If momentum space is curved, space-time is just as observer-dependent as space, and the invariant arena for classical physics is phase space. Now, there seem to be two motivations for this phase space realism in these papers. And the first is based in part on the claim that descriptions of physical systems in terms of their energies and momenta are more fundamental than descriptions in terms of their spatiotemporal properties. So here are some relevant quotes. Our most fundamental measurements are the energies and angles of the quanta we emit or absorb and the times of those events. Judging by what we observe, we live in an energy momentum space, not in space-time. What we really see in our telescopes and particle detectors are quanta arriving at different angles with different momenta and energies. These observations allow us to infer the existence of a universal and energy-independent description of physics in a space-time only if momentum space has trivial flat geometry. Now, another type of motivation for phase space realism that appears in these works is based on an analogy between the relativity of simultaneity and relativity of locality. Relative simultaneity can be explained by an appeal to an invariant spatio-temporal interval, right, that can be decomposed into separate spatial and temporal intervals, but in an observer-dependent way. Right? So analogously, relative locality can supposedly be explained by appeal to an invariant phase space interval that can be decomposed into separate spatio-temporal and energy momentum intervals, but again in an observer-dependent way. Right? Quote, physics takes place in phase space and there is no invariant global projection that gives a description of processes in space-time. From their measurements, local observers can construct descriptions of particles moving and interacting in a space-time, but different observers construct different space-times, which are observer-dependent slices of phase space. So there are at least two concerns with the second motivation. First, we might agree that spatio-temporal intervals are relative, whereas phase space intervals are absolute. But this doesn't necessarily imply that phase space descriptions are more fundamental than spatio-temporal descriptions. Any more than the ability to encode spatial and temporal properties in an invariant spatio-temporal interval doesn't necessarily imply that spatio-temporal descriptions are more fundamental than spatial or temporal ones. You can adopt a dynamical relationalist interpretation of special relativity, for instance. Well, the second concern is with the extent to which the analogy between the relativity of simultaneity and the relativity of locality holds. So the relativity of simultaneity involves a distinction between absolute and relative quantities. The relativity of locality, on the other hand, seems to involve a different sort of distinction, one between global and local quantities. So I take it it's supposed to be an effect that depends on the curvature of momentum space. And curvature is only pronounced on a global scale. You can always choose a neighborhood of a curved Riemannian manifold in which the curvature is, for all practical purposes, 0. Right? So this seems to indicate that the relative distinction here is between a local and a global property. The upshot of this discussion seems to be that the motivations for phase-space realism that are expressed by advocates of relative locality perhaps at most uphold momentum space realism. Okay, so in conclusion, I've looked briefly at two principles of quantum gravity in the context of the condensed matter approach. I've suggested that both versions of this approach should aspire to be asymptotically safe, but I've questioned whether an asymptotically safe theory can also be considered an effective field theory. To support such a claim may require fleshing out a notion of emergence that's appropriate for effective field theories. I've also suggested that both versions satisfy relative locality to the extent that they encode relevant quantities in momentum space topological invariants, and these invariants can generate non-trivial momentum space curvature. However, whereas advocates of relative locality maintain that it supports phase-space realism, I've suggested that perhaps a more nuanced claim should be restricted to what might be called momentum space realism, namely the claim that momentum space is more fundamental than space-time. So I'll stop there.
Good. We've got about 8 minutes for questions. Take them, or do you want me to be done? Okay. Questions? I'm back.
Can you refresh me about why relative locality is a desirable thing? It seems crazy and I wouldn't want it in my view.
You say crazy like it's a bad thing.
Well, let's see. Some of the one motivation that advocates give is an appeal to experience, basically. They claim that what we actually observe are properties associated with energies and momentums as opposed to spatiotemporal properties. So they would say, regardless of whether or not you think it's a bad thing, it's the sort of thing that's supported by the empirical evidence.
It seems like we observe things that are both spatial, temporal, and momental. I don't know. Yeah.
Jeremy, and then I'll go to Daniel.
Well, this is a finger. I'm afraid I don't know anything about relative locality, but is it meant to be a way of thinking about classical mechanics as well? Because these points about energy and angle are what we measure would apply in a classical physics and metaphysics. But if it does apply classically, what does it say about, for example, Darboux theorem, that every symplectic manifold is locally a cotangent bundle? I mean, there is an internal mathematical drift in symplectic manifolds towards thinking of a preferred projection. Or does it not work with a symplectic manifold? Do you use classical mechanics without a symplectic manifold?
I don't think so. I'd have to think about that, actually.
Why don't we go on?
Main point is the addition of metals.
It's not a bundle. It's not a bundle.
It's not a bundle.
Okay, sorry. Daniel.
So it's more reply to that question about the motivation for relative locality. I'm not a supporter, but there are a bunch of motivation that you can come up with coming from quantum gravity. One is that So if you just look at the particle coupled to quantum gravity, it gives one realization of relative locality.
Did you want to respond to that, or do you have anything to say?
No. Well, I think another motivation is, to your intuition that we really observe spatiotemporal properties as opposed to energy momentum
Well,
properties.
and both. I mean, it seems like both, right? But, exactly.
I think the advocates would say that the reason you think you measure spatiotemporal properties is because you're using instruments that have very low energy and very low momentum.
Those corrections are plot scale suppressed.
Any other questions? Did you want to come back to Nick?
Yeah, so can you go in the slide? Can we go back to the bit that you said that led to saying? I'm going back to my original question, but we've now said yes to asymptotic safety in these theories. Could you go back to the slides where you spelled that out a little bit? I guess it's sort of towards the beginning. Is there something in there that's going to answer my question? Yeah, so just the question was...
Fixed point that we...
Yeah, so on asymptotic safety, we know, right, so, okay. It wasn't that kind of thing. We know, right, so QCD is asymptotically free, so it's the Gaussian fixed point. It's the UV fixed point, but, for a long time people didn't think GR quantum field theory had a fixed point at all, and I guess there's recent work now that people think they found a fixed point, but it isn't Gaussian fixed point. I guess you know it's not that. Okay, but your discussion wasn't involving some technical response to that sort of concern. It's about, it's more to see. Okay. Did you know this paper, Joe? I'm thinking of some of the work you've done recently on these kind of questions about Jonathan's paper.
Yeah, I don't know anything about modern asymptotic safety gravity.
One more. Let's see if we have anybody else, and if not, I'll come back to you. All right, we'll come back. Danielle.
So, regarding the question about asymptotically safe theories being possibly effective field theories as well. And I don't have the answer, but I've asked people in asymptotic safety whether they ever applied the renormalization group techniques they use to hydrodynamics, to scalar field hydrodynamics in condensate, like Jones-Pitayevsky equation, or even to known effective field theories like the theories of Mason and so on. They say they didn't, but they also say that it's well possible that if they do, they will find that they are asymptotically safe. So I think that they would agree that the fact that the theory is asymptotically safe only means that it could be fundamental, in the sense that it doesn't internally break down. But it doesn't exclude that the possibility that you just consider only some of the true degrees of freedom, and that there will be other degrees of freedom that they didn't take into account that will make the theory effective just because of that, just because they didn't consider the right degrees of freedom, like in methods. So I would agree with that with your conclusion.
Nick, and then we'll...
I think, so Bob Weingart and I had a paper back in the late 90s that, was sort of made, I guess, in response to the Challenge-Schwaber paper. And that's kind of the response we were making in that paper. That, asymptotic safety means, could be, it could live in a continuum space-time, it could be fundamental, but not necessarily. But surely, presumably, physicists think the answer to your question has to be yes, right? QCD is asymptotically safe, but I'm guessing most people think it's an effective theory to something in loop quantum gravity or string theory or something, right? So that doesn't mean that they shouldn't think about that question more carefully, as I guess you're suggesting here, but it seems that's what people, right? Isn't that what people have to think? QCD's
even simpler because
it's asymptotically safe, and
it's actually asymptotically free.
Right.
It's even simpler.
Yeah. But everyone thinks it's an effective field theory, right?
Well, quickly, Jeremy, and then...
Just a finger about this
Yeah.
word fundamental. I think for reality in all its myriad glory, no doubt QCD is not fundamental, right, because of gravity. But if we're playing the interpretive game of wanting possible worlds to be truly mathematically consistent, I think that's the sense in which people will say QCD is an effective bit, precisely because they believe, as Topology put it, that if you took a Japanese monk and put him in for 10 years in the monastery and required him to gather all the papers off the archive, you could bet better than even money that 10 years later he might come out and prove that QCD exists. I mean, it's not really known, but it's all